Hello friends, welcome back to our channel Mirror Neuron, which means watch and learn. And today we are going to talk about a very complex and tongue twisting word, but the concepts are very simple. Okay, just repeat with me. Homoscedasticity. Okay, practice it 1,000 times so that you can memorize it. Just kidding. All right, homo means same, scedasticity means scatter. Now that you know this, it is so simple. Same scatter across the dataset. That's all that it means. Okay, now let's take an example. Father's height in the x-axis and daughter's height in the y-axis, right? And if I take an example here, say I have the data for say 1,000 families, yeah, and I have measured the height of fathers, and I found few of them to be 60-inch tall. And I have measured the height of their daughters, and I found some data, and I have plotted it in this scatter plot. And I can see their daughter's height range, say something around 58 inch to say 66 inch. Okay. Similarly, I have some other fathers who are quite tall, 6 feet, say 72 inch, and I have measured their daughter's height as well, and say they also range between say 72 inch to say 77 inch. Now what I can see is, if I take them as a separate distribution for the father and daughter's height at father, which is 60 inch, and for the father and daughter's data where father is 72 inch, I can see that the daughter's height's standard deviation, if I see the spread of fathers who were 60 inch, say is roughly around 3 inch. And similarly, if I take the daughter's height's standard deviation for fathers who are 72 inch, and I get roughly around say 3.2 inch, what do I see? I see that the spread of the daughter's height for different fathers' height is quite same. And if our data depicts this kind of similarity, we call those kind of data as homoscedasticity. All right, quite simple, isn't it? Now you must have already guessed that what heteroscedasticity would mean. It would mean that the spread across the data is different, and that is why it is called as hetero, which is different scatter. Let's look at a quick example. Okay, so we can see that from this graph, when we have age in the x-axis and income in the y-axis, if the data or the scatter plot looks more like a cone, like that cone shape. Of course, I hand drawn it just to see that the income increases with age, right? We all know that a baby who is 1 year or 2 year old is not making money at all, and people who are at the age of at the 60 or 75 years, they have maybe had a very successful business or job, and they made a lot of money. So if you see the spread, right, keeps increasing and keeps changing. So if I take the standard deviation of income for babies who are, or kids who are 3 years old, I will get say maybe a couple of $100. Say they are like child actors and they made some money, and the spread is quite small. And if I go and to the age around 60, I can see the standard deviation could be in thousands and thousands of dollars. That means if I go from age 0 and 1 years to all the way to 75 to 80 years, the scatter is not constant like we saw in the height of the fathers and daughters relationship. Right here it keeps changing. And what happens is, when the dependent variable and the independent variable had such shape, like a conical shape, what happens, the prediction error also keeps changing for different age group in this case. And that is why a regression method kind of analysis is not going to help you in the long run. And that's where the challenge of heteroscedasticity comes in. Alright, so I hope you have understood the difference between homoscedasticity and heteroscedasticity, and this has been quite pending. I thought of that this complex term should be simplified. I hope you have liked the video, so please subscribe to our channel for other tutorials. Thank you and have a nice day.